This hydraulic circuit has about 10 different components. The whole function of the circuit is to turn this spinner plate. The motor will turn the spinner plate, fertilizer will be dropped onto the spinner plate, and the spinner plate will send the fertilizer all over the place. The components that we've got in this particular circuit are the hydraulic reservoir, a suction filter, electric motor, hydraulic pump, pressure gauge, pressure relief valve, which is a safety device, directional control valve, which in this case has two positions and it's a three-way valve, the hydraulic motor, a flow control valve, a check valve, which has got a 65 psi spring, and the return line filter. To start operation, we'll turn on the electric motor. With the electric motor turned on, the pump will begin to turn. As the pump turns, fluid will be pushed from the reservoir through the suction strainer into the pump. From the pump, it'll go to about 3 places simultaneously. It will go up to the pressure gauge, it will go to the pressure relief valve, and it will go up to the directional control valve. The directional control valve in this position will take the oil and it will send it out through that port, and that fluid will go back through the return line filter and back to tank. It's possible that some of the fluid will go out this way. It'll come up to the check valve and be stopped. Can come up through this way, might go through the flow control valve backwards and come back over here and come to here and be stopped. Any fluid that would go through the motor and come to the check valve would then be stopped because we've got fluid on both sides and the check valve will be held closed. Once the electric motor is turned on and the pump is running and sending fluid through the circuit, we will shift the lever on the directional control valve and move the directional control valve into a position like this. Now, the fluid that is pushed out of the reservoir through the suction strainer into the pump, and from the pump to the gauge and the relief valve will go through the directional control valve and will go over to the motor. That will cause the motor to turn, and discharge oil will come out of the motor, go through the check valve, and go back through the return line filter to tank. If we want to control the speed of the motor, we will just open up the flow control valve and allow some of the fluid to go through the flow control valve, back through this line, and then back to tank. Now, just picking numbers out of the air, which have absolutely no basis on anything, but if we were to have a 10-gallon per minute pump, and if the flow control valve were to be closed so that no fluid could go through it, we might assume that the hydraulic motor will turn at 1,000 RPM. If we open the relief valve so that approximately 5 gallons per minute can go through the flow control valve, which is about half of the flow, then we have 10 gallons coming from the pump, 5 gallons going through the flow control valve, and 5 gallons per minute going through the motor. Because we have only half of the flow going through the motor, instead of operating at 1,000 RPM, we find that our motor will operate at 500 RPM. So the more fluid that we allow to go through the flow control valve, the slower the motor will run. And as we reduce the amount of flow going through the flow control valve, the motor will go faster. There are a fair number of people who instead of putting the flow control valve here to bleed fluid off, we'll take the flow control valve and they will put it on the outlet port of the motor, so that as fluid goes through the motor, if the flow control valve is wide open as far as it can go, full flow from the motor will go through the flow control valve, through the return line filter, and back to tank. And then if you want to slow the motor speed, you'll take the flow control valve and you'll start cranking it down. The concern with doing this is that when we have a pump that is putting out a certain amount of fluid, and let's just pick 10 gallons per minute for the sake of argument, the fluid coming out of the pump, going up to the motor, and going through the motor and back to tank is generated just enough pressure to do the work. So let's say in this particular system, if we put 10 gallons per minute through the motor, we're going to turn that spinner at, we'll just pick a number out of the air, 1,000 RPM. And we're going to operate at, once again picking a number out of the air, let's say 250 psi. So I've got 10 gallons per minute going through the motor, which is going to turn the motor at 1,000 RPM, and it's going to take about 250 psi to do the work of spinning the spinner and distributing the fertilizer. Now, if I start to crank down on the flow control valve and reduce the amount of fluid that can go through it, which will slow down the speed of the hydraulic motor, we're going to have a bit of an issue. Let's say that we set the flow control valve to 5 gallons per minute, which means half of the 10 gallons per minute can go through the motor and back to tank. But where does the other 5 gallons per minute go? Well, as soon as we start cranking down on this particular flow control valve, the pressure starts to build because we've got 5 gallons, we've got too much oil coming out to go through the flow control valve. And as pressure starts to build, it's going to go to 250, 300, 400, 500, 600. When it gets to 750 psi, parts inside the relief valve shift and the excess oil flows over the relief valve and back to tank. So that if we were to set the flow control valve at 5 gallons per minute, we would then have 5 gallons per minute spilling over the relief valve and 5 gallons per minute going to the motor. But our system pressure, instead of being the 250 psi it takes to do the work, would be at our relief valve pressure of 750 psi. And if we were to take this flow control valve and instead of having it on the outlet port of the motor, we would put it on the inlet port of the motor, we have the exact same issue. If we have a 10 gallon per minute pump and we set the flow control valve for 5 gallons per minute, then we only allow 5 gallons per minute to go through the flow control valve, which means the other 5 has to go someplace. And what will happen is the system pressure will build, and at relief valve pressure, 750 psi, will spill over the relief valve and back to tank. And in essence, we're generating the pressure. We're doing absolutely nothing with it, so it's getting turned into heat. We're wasting money, we're wasting energy, and we're creating heat, which can cause our system to overheat and cause problems. Now, if we go back to the original setup that we had, where the flow control valve was bleeding fluid off, let's say that we set our flow control valve for 5 GPM, and our pump is once again putting out 10 GPM, and it takes only 200 psi to do the work. Now we have 5 gallons per minute that is going up, going through the relief valve and spilling back to tank and doing no work. So we're generating some heat there. And we have 5 gallons per minute that is going through the motor and turning the motor. So once again, if at 10 gallons per minute we were spinning at 1,000 RPM, at 5 gallons per minute we'll be spinning at 500. But notice that our gauge is showing only the amount of pressure that it does to do the work. So we're at 200 psi, and instead of spilling 5 gallons per minute over the relief valve at relief valve setting, we're now spilling 5 gallons per minute over the flow control valve at working pressure. So we're still generating some heat, but we're not generating as much heat. And if we were to, instead of set this at 5 gallons per minute, let's say that we set it at 1 gallon per minute. So now we've got 9 gallons per minute doing the work and 1 gallon per minute spilling over. We're still at 200 psi. So we're saving a tremendous amount of energy, and we're reducing the amount of heat generated by bleeding off through the flow control valve instead of trying to control the flow of the fluid before the motor or after the motor. The only other thing that we should probably go over is the function of the check valve. In an application like having a spinner, it's possible that the fluid with the bleed off circuit, instead of going through the flow control valve, would find it just very easy to go through the motor and keep on spinning the motor. So if we tried to open up this thing just a wee little bit, let a gallon through or a gallon and a half through, we might not see any kind of change in the speed, because it's still going to be easier for the oil to go through the motor than to go through the flow control valve. But if we put in a check valve that has a 65 psi spring, then we've got a 65 psi back pressure coming out of the motor and going through the check valve, which ensures that the fluid is going to go through the flow control valve instead of going through the motor as we open it up. So the function of this check valve right here is to make the flow control valve more accurate in the control of the speed. And I think that takes care of everything on this circuit.